Hello everyone, and welcome to Euclid Book 1, Proposition 9. So we are back now into a construction proposition, which are the most fun, of course, so we'll just go ahead and just jump straight in. So Proposition 9 says the goal is to bisect a given rectilineal angle. And we start off with let the angle BAC be the given rectilineal angle. So go ahead and draw yourself an angle BAC, which I'll go ahead and do here. So BAC, there we go. That is our angle BAC. Euclid says, thus it is required to bisect it. Let a point D be taken at random on AB, easily enough. Let a point D be taken at random on AB, there it is. And let AE be cut off from AC equal to AD. In other words, we want to cut off AC so that AE is the same length as AD. Euclid says we can do this by Book 1, Proposition 3, but it's very easy to do just by drawing a circle. So draw a circle with center A, radius out to D. And where that circle intersects AC, that is your point E. Yep, there we go. And since all radii of the circle have the same length, we have now satisfied AD is equal to AE. There we go. Euclid continues. Let DE be joined. Easily done. Let DE be joined. Not like that, though. Let DE be joined. There we go. And then he says, and on DE, let the equilateral triangle DEF be constructed. So we've done this several times now as well. Remember, you do this by drawing two circles. One circle that starts at D out to E. One circle that starts at E out to D. There we go. And then where those circles intersect down here below, that is your point F. Go ahead and connect D to F and E to F. And since all three of these lines are radii of sort of identical circles, this is equal to this is equal to this, and we have in fact constructed an equilateral triangle. And then Euclid says, and let AF be joined. So go ahead and let AF be joined. Yep, there we go. And then we're basically done. There we go. Euclid says, I say that the angle BAC has been bisected by the straight line AF. So we're in fact on AF does in fact bisect the angle BAC, but Euclid is now going to argue by looking at this triangle right here. I don't know if I need to draw that for you to make it clear. There we go. So he's going to look at this triangle on the left right here, right there. And he's going to look at this triangle on the right here, that triangle right there. And argue by side, by Proposition 8, that this triangle on the left is equal to this triangle on the right, which means all their angles are also equal. So this little angle right here is equal to this angle right here, which is what we need to prove to finish the proof here. But it's also true that this angle right here, right, is equal to this angle right here, but we don't care. And it is also true that this angle right here is equal to this angle right here, but again, we don't care. But we do care about the top. But if the triangles are equal, congruent triangles, all those angles will be equal. So he finishes the proof. For since AD is equal to AE and AF is common, the two sides DA and AF are equal to the two sides EA and AF respectively, and the base DF is equal to EF. So he argues, in other words, that this line equals this line. Since that was one of the first things we did was to make sure AE was equal to AE. So this line equals this line, and this line here equals this line right here, since this is an equilateral triangle. And finally, this line, of course, equals itself. It's common to both triangles, and so we have, in fact, finished the side proof that this triangle is congruent to this triangle. There we go. So Euclid finishes, and the base DF is equal to the base EF. Right. Therefore, the angle DAF is equal to the angle EAF. So therefore, this angle right here, right there, is equal to this angle right here, right there, which is what we needed to finish the proof. Then Euclid says, therefore, the given rectilineal angle BAC has been bisected by the straight line AF, QEF. And we will use this proof again in many proofs in the future.